Thanks, Dave. And thanks to you all for sticking with me. We're going to have a big group photo tomorrow, but everybody say cheese. Say local rings. Noetherian rings, exactly. Okay. Thanks. So the first order of business is a correction. I misattributed a result in my lecture yesterday. There were two. One was that if the completions of two modules are isomorphic, then the modules are isomorphic. I said that was an EGA. That's correct. But then I said that this fact, that if the completions are summands of each other, then the originals were summands of each other. I said that was also EGA. That's not correct. This is due originally to Roger Wiegand using a result of Bob Guralnik's. So I wanted to make sure I got that corrected. Let's remember where we were at the end of last time. So if R is a one-dimensional local domain, domain here is an important word, with reduced completion, then a finitely generated R hat module N is extended from R if and only if it has constant rank. Constant rank here means that when you localize at a minimal prime, the thing you get is always a vector space of the same dimension, no matter which minimal prime. So I'll say at the minimal primes. This was a consequence of the theorem of Lee and Odenthal that I wrote down last time. So let's see what you can do with this. Suppose you could construct somehow, we don't know how yet, that is in about 15 minutes, we'll talk about how, but suppose you could construct a ring R, as in over there, as above, no, as to the left, such that the minimal primes of R hat, there are just two of them. Suppose you could do this. You could construct R and R hat so that the minimal primes of R hat was just 2, and some R hat modules sorry, let me say one more thing before I go on to that. So if we could do this, then for an R hat module N, that is, N R hat module N is extended if and only if its ordered pair of ranks which that's far too much to write, so let me just write rank N. If its ordered pair of ranks are just AA for some A. Now suppose we could construct some particular modules. And let me make sure I get the letters right or I'll confuse myself later. Let's say U and V and W and X with the rank of U equal to 2, 0, so that's its ordered pair of ranks. The rank of V, 0, 2, rank of W, 2, 1, and the rank of X, 1, 2. Suppose we could. We don't know that we can yet, but suppose we could. Yes, in decomposables. Well, thanks. Then, of course, none of these, excuse me. None of these is extended because they don't have constant rank. But you can, if you put them together, let's see, how can we put them together to get things of constant rank? If we took U direct sum V, so I'll write here on this line the ranks. This would have rank 2, 2. U direct sum V. What else? We could also do V together with 2 copies of W. Does that work? Yeah, it would have rank 4, 4. We could also do W plus X, and we could also do U plus X 2 copies. And again, these would have constant ranks, so these are all extended. U plus X? W plus X. Did I screw it up? Oh, yeah. No, I wanted. Oh, it's 3, 3. I just wrote the wrong thing. Thanks. Thanks. So these are all extended from R modules. Let's say A and B and C and D. So in other words, the completion of A is isomorphic to U direct sum V, and so forth. And now look at, let's see, if I take A and 2 copies of C, and I complete that. This is a big moment. Let's see if I got it right. So completing A gets me U plus V. Completing 2 copies of C gets me 2 W's and 2 X's. And of course I can shuffle those around. Using the associative law for modules, which apparently is a thing, but we'll just go ahead and use it. And this, of course, is what? Is C plus, have I got it wrong? I got the U and the V mixed. I got the U and the V in the wrong places. There we go. So now this is B direct sum D completed. And because we have these two finally generated R modules whose completions are isomorphic, they themselves are isomorphic. And so here we have a failure of Krull-Schmidt that we have built out of this machine. Of course, everything up to here was fine without the modules being indecomposable, but to conclude the failure of Krull-Schmidt. You do need a little argument. I was going to carefully not discuss that. And as two further exercises, construct failures of the form. Well, here we've got A plus 2 copies of C, so go ahead and construct a failure of this form, which, if anything, it's easier. And then go ahead and try to do one of the form A plus B isomorphic to C plus D plus E, using this same technique. I will collect those at the end of Friday's talks. Okay. So all that was contingent on the assumption that we could construct a ring and construct these modules. So that's the last thing I want to discuss. And this is a construction due to Roger in 1891, I think. Older? I think it's about 2000. Okay. And actually, I'm going to take this opportunity, maybe in colored chalk? Sure. I'm going to insert here a reference for not just this next part, but everything I've said in the previous two lectures and everything I'm going to say in the rest of today. A project codenamed Book, when Roger and I were working on it, which is a book called Cohen-Macaulay Representations, which, as I say, everything I'm saying is drawn from this. In fact, it's drawn from chapters 2 and 3, which I think are some of the prettiest chapters in the book, and I can say that because Roger wrote them. And also, it gives me a chance to say here publicly, for posterity, that this project has been the highlight of my professional career so far. The fact that people use it and enjoy it brings me joy every day, and the fact that I got to do it with Roger is one of my cherished memories in mathematics. So, thanks. Now, back to, oh no. Disaster. I lost Sean's chalk. I'm sorry, the rest of the lecture is canceled. No, seriously. Did I? Oh, Sean, I'm so sorry. We'll find it after. All right. So here's the construction. So let's fix an integer s, and let's take s distinct rational numbers. And let's consider the ring of polynomials in the same number of variables over the rationals, mod x1 minus t1 to the fourth power, why fourth? We'll get there. x2 minus t2 to the fourth, xs minus ts to the fourth. So of course the Chinese remainder theorem says that this is isomorphic. Well, do I want to say that yet? Yeah, let me not worry about that. And let's let W in the polynomial ring be the complement of the union of those ideals. And let's define a ring R as a pullback. So here's what I want to do. Let's, down here in the bottom, let's put q bracket x1 mod the fourth power of this monomial up through q bracket xs mod the same fourth power. Then the localization maps to this by killing each one of these. We've localized so that these height 1 ideals are the only maximal ideals in the localization. Over here, embed the rational numbers diagonally, and then R is the pullback. Then some facts about R. First of all, R is a one-dimensional local domain. This thing here is sometimes called the conductor square for R. This is the integral closure of R. These are sort of generic facts about pullback diagrams of this form. We won't need all of this. I'm just going to point out the facts that we do need. So R is a one-dimensional local domain. R hat is reduced and has exactly S minimal primes. Oh, I found it. Then here comes something that will take a couple of minutes to explain. Since each factor each of these factors down here in the lower right-hand corner, of course, is isomorphic as a Q algebra just to this, just do a little change of variable. Roger shows that the Artinian pair, which I'll try to explain what that means, the Artinian pair that is the bottom row here admits indecomposable representations V into W. Whoops, wrong. I shouldn't use W. Let's try U into V. Of every possible rank, R1 up to RS. Okay, so this takes some explaining because I've used words that I haven't defined at all. So let me parenthetically try to explain what this means. So a representation of a pair of Artinian rings is U into V, so one of these things, where V is a finitely generated projective B module, so the bigger of the two Artinian rings. U is an A submodule and if you extend scalars, if you hit U elements of B, you get all of V. So this is a technical notion that I don't really expect you to absorb right away. It's kind of, if you're familiar with the matrix problems of the Russian school of representation theory, it's a jazzed up version of matrix problems that allows one to understand representation theory here over this one-dimensional ring in terms of representations not of a single Artinian ring but of a pair. It's a technical tool that I guess is essentially due to Drozd and Reuter. This bullet, this fact where it says, since that's true, Roger Wiegand shows this is technical, delicate, hard, and you're likely to screw it up the first 3 times you try. I certainly did too. Okay, so that's 3 bullet points. I have one more. Let me see if I can sneak it in here. The power of this conductor square is that a representation of the bottom row gives you a module over the pullback. So the consequence there is, so I'm just going to say so. It's not clear that that's a direct consequence, but so R has indecomposable modules, even indecomposable torsion-free modules let's call them M. Oh, sorry, let me say R hat here. R hat has indecomposable torsion-free modules N of all ranks R1 up to RS. At least one of them should be non-zero or there's no content here. I never thought I would say this board needed to be bigger. So the consequence, I guess I'll erase the diagram now. The consequence is that this construction realizes any divisor closed subgroup of a free semigroup of finite rank as at M for some M. So let me state the theorem a bit carefully. Sub-semigroup, yes, thank you. As I say, let me state it carefully. So let's let S inside the natural numbers to the N be a divisor closed sub-semigroup. And let's assume S is, and I'm not going to define this, I think you can probably guess more or less what it means. This subsemigroup is cut out of the free subsemigroup by some equations. Let's just say M of them. Then the construction with M plus 1 minimal primes, so S is M plus 1, gives a ring R and an finitely generated R module M so that the diagram consisting of S sitting inside n to the n, here add of M, and here add over R hat of M hat, these things are isomorphic and fitting into a commutative diagram like so. So that's it. That's the big goal I had to get to in today's lecture. I have a little time left, so I want to say just a couple of words more about semigroups, hoping that I don't steal too much more of Nick's talk, since I already gave half of his lecture yesterday, he told me. Sorry. Luckily, he gets to write a whole new talk. This allows us, or allows Roger, or whoever wants to, I guess, to characterize the semigroups arising as add of M for any R and M. In other words, we can intrinsically characterize whether a semigroup can arise in this way for any local ring R and any module M. And let me tell you what they are. A positive normal semigroup is one such that, first of all, it should be finitely generated semigroup. Secondly, it should be isomorphic to a sub-semigroup of a free. And third, this is the real content of the definition. If A in ZS, so what is this? So S lives inside the natural numbers, but if you extend scalars to allow negative numbers, you get the group associated to S. If A satisfies NA living in S for some integer n, then A was actually in S. And it's an exercise, not an exercise I'm assigning this time, but one in Bruns and Herzog 6.4.16, that such things are exactly well, let me tell you what they are exactly. The following are equivalent for S. S is positive normal in this sense. Secondly, S is the intersection of a group G is a subgroup of n to the m. And I should maybe put here the z to the n, thank you, yep. And third, S is the intersection of a vector subspace. I wrote M there, so I'll write N here. So these are the ones that arise from intersecting subgroups of the integer lattice or intersecting subspaces of the rational cone. Notice this M is different from this N. They don't have to be the same. And so finally, the last theorem I'll discuss follows from the construction that the following are equivalent for a semigroup S. First of all, S is positive normal. Second of all, S is isomorphic to add M for some, well, let me say add Rm, for some local ring R and module M. And third, S is add of M, not just for any local ring, for some one-dimensional local domain. And torsion-free M. So already in this very restricted setting, you get all of the semigroups you could possibly ever get. And I think I'll go ahead and stop here. Thank you very much for your attention.
This is in a 2001 paper. It's not all that old. I have one. Your construction, you do need to be domain.
Well, you can get away with a domain. If you allow R to have more than one minimal prime, you could a priori get even worse behavior. But what this says is you can get all the bad behavior you need with domains.
Yeah, because many private products are not even reduced, right?
Sure.
And they have limited dimension there to one.
Right.
So
But you do need the completion to be reduced for this machine to work. Right. So R specifically has to be reduced as well.
yeah, is it possible for R to be regular? That's more amenable setting of being a domain and completion being okay for R to be regular? Because I guess it would be equivalent for P or Q to be contracted from R.
I think if R is regular, probably the whole machine collapses.
It depends on
And
splitting in the completion.
yeah.